I uploaded my own code into the International Space Station 400 kilometers up in space. And today I'm gonna show you exactly how I did it and how you can pull it off as well. So a few months ago, I was surfing the internet and decided to check on the Raspberry Pi website for any cool news. And there, I stumbled upon something called Mission Space Lab. Apparently, it was a challenge in collaboration with the European Space Agency, which let students run scientific experiments remotely on some Raspberry Pi based devices which had been brought to the ISS on a rocket back in 2015. Of course, I wanted in as well, as I was thrilled to have my code run in space, in the most expensive structure ever built by mankind. However, it turned out the submissions had been closed a while ago. I was too late. But then, a ray of hope hit me. When, in my disappointment, I returned to the AstroPi homepage, there were two different missions, Mission 0 and Mission Space Lab. And while the latter was grayed out, Mission 0 was still in the submission period. But what is Mission 0? Well, apparently it was like the noob version of Mission Space Lab, targeted at younger students and absolute beginners. It was about using the Sense Hat, a board that included a bunch of environmental sensors and an LED matrix, included within the AstroPi devices, to display a custom 8x8 pixel art for the astronauts to see. Or at least, that's what they expected students to do. I went into it without much expectation, planning to maybe send an encrypted message to the astronauts, but I'd never used a Sense Hat, so I needed to learn its Python module's functions. Now, instead of following the cringe class activity instructions, I went straight to the PyPy repository for the Sense Hat module and quickly found the API reference for it on Read the Docs. And oh boy did things change! I started to realize I couldn't only send a pixel art. I had access to temperature, humidity, pressure, light and color sensors, a fully equipped IMU sensor with a gyroscope, accelerometer and a compass, a joystick and a ton of functions for the LED matrix, including text printing. So I was determined to take them by surprise. I was determined to make the absolute most elaborate code Mission 0 had ever witnessed. My idea? I was gonna make a full freaking video game. So I went to the drawing board. Now, the main problem I had was that I only had a screen a measly 8 pixels wide. That is not a lot, and it would be the main limiter to the complexity of my game. So I needed to be smart with my design. I ended up settling for a 2D top-down banner/puzzle video game where you had to avoid obstacles. And that's cool and all, but now I had to actually pull off coding a video game with no kind of visualization modules. And here's how I did it. So the code starts with a few initialization functions and variable definitions, as always. And here's where I introduce a variable I'll use later to signal where the character is dead. Now, here I introduced my first screen. To display something on the LED matrix, you pass an array to the setPixels function. So here I created all the arrays for the different levels, with each item containing the RGB values for its pixel. Then, I had to store the locations of the different interactables, like the obstacles and exit, for each level in lists, to be able to later use them in logical operations to, make the game work. I also stored the indices of the left and right boundaries, and you'll see why they're important later. Finally, I introduced a variable to store the location of my character, again as an index to use on the pixel arrays. But now I needed a way to make it move. Now, I could have used the joystick for this, but come on, that would have been too simple. I had a whole IMU in my hands and I was gonna use it. So I decided that the astronauts would be able to control the character by tilting the device, which was much cooler. And here's where the actual game begins. It first enters a loop for level 1, and here you can see the logic for the movement mechanism. If the pitch angle was less than 70, so if it was pointing up, and the character position was an index greater than 7, so it was not already in the top row, the character position index would be decreased by 8, or a whole row, to move it to the pixel above. If the pitch was more than 110, so it was pointing down, and the character position was less than 56, so it wasn't in the bottom row, the opposite would happen. Then, if the yaw angle was between 20 and 90, so pointing left, and the character position wasn't in any of the indices I had previously defined as the left boundary, then it decreased the character position by 1, moving it to the left, and the same thing for the right. Then I stored the pixels from the lobby into a variable called pixels, but changed the item at the index of the character position for a white pixel, before continuously passing that to the setPixels function. This would run every half a second, updating the character position based on the tilt of the AstroPie. And finally, if it detected that the character position was in any of the pixels I defined as the exit, it would break the loop and go on to the next one, level 1. Here, I used the same movement system, but this time there were obstacles, represented by the red pixels. If the character happened to be in one of the indices defined as obstacles, it would print game over and the loop would break after setting the dead variable to true. If the character was in pixel 15, the exit, represented by the color green, the loop would break as normal and continue to level 2. Now, in level 2, the layout gets a bit harder, but now it starts by checking if dead is true. If it is, it skips the level 2 loop entirely. If it's not, then the fun continues as before. And finally, after the same death check, we have level 3, which nicely follows the difficulty curve of the game. However, this time, the obstacles are completely blocking the exit. You need to first grab the key, represented by a yellow pixel, and once the character position is in its location, the level 3 array and the list of mine locations will be changed to remove one of the mines blocking the way. Now, you can finally exit the level and win the game. If, after all that, the dead variable is false, it'll tell you you've won. Otherwise, and this is what you'll skip to if you did die, it prints a thank you message to the astronauts, and finally my YouTube username. Hey, how many people can say they promoted their channel in space? If any of the ESA guys is watching this, tell me in the comments if you managed to beat my game. However, before I could submit my code, it turned out I had to do a test run which had to meet some requirements. For example, the code had to run in less than 30 seconds, I had to use the color sensor, and personal information like social media handles was not permitted. I had a big problem. The color sensor thing was easy. I simply added a screen at the end with all the pixels RGB values set to the red, green and blue values detected by the color sensor from the environment at that moment. However, I needed to prove to the program that my code could be finished in 30 seconds. So it was time for a death percent speedrun. As soon as I spawned in, I rushed for the lobby exit and immediately unalived myself with one of the level 1 obstacles. Then, all that was left was to impatiently wait for the end screen to finish and hope that it did before the 30-second mark. And it did! And as for the social media handle, I'm sorry, I was not about to remove that. Now, I had to give my one-person team a name, and I called it 137, of course. I submitted my code with a bit of fear that they'd reject it for several reasons, and then all I had to do was to wait and hope for the best. Then finally, 2 months later, I got the results. My code had been accepted! Unfortunately, even though I wanted to know how it went, the certificates with the data about the run would only be sent in June. And a few days ago, less than a week after my birthday, it finally arrived. According to it, the program ran at the coordinates 24.5369, 136.229, which is right around the middle of nowhere, on the 14th of May. Mission accomplished. This was a really fun project, and I think the fact that anyone can send their code to outer space with this is absolutely brilliant. Oh, speaking of, this video was sponsored by what's officially my first sponsor, Brilliant. Brilliant is a learning app that helps you get smarter every day, with thousands of interactive lessons in math, science, programming, data analysis, and AI. These lessons let you actually interact with the concepts you learn, which has been proven to be 6 times more effective than watching lecture videos. They're made by an award-winning team of teachers, researchers, and professionals from Stanford, MIT, Caltech, Microsoft, Google, and more, and they build your understanding of complex topics from the ground up and develop your problem-solving skills. A really strong feature Brilliant has is how it encourages daily learning. It makes it really easy to get a habit going, and habits can be really powerful. Through only a few minutes a day, you'll be learning a ton before you even realize it. And if you also want to participate in the Astrobyte challenges but don't know how to code, you're in luck! Brilliant's newly updating programming courses are a great way to build a foundation in coding, get experience with real-world applications, and learn to think like a programmer. With them, you can get familiar with Python and start building programs on day one. You'll also be developing your problem-solving skills and your intuition with computer logic. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/flamethrower or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. All that said, thanks for watching and I'll see you in the next one.